All right, welcome physics. We're going to talk a little bit about a concept today called impulse and momentum. So if you would get the handout I provided for you for notes, and if you would just kind of follow along as we take notes today, and I will have you submit them. Here we go. So let me pull up the notes real quick. All right, here we go. So if you would kind of follow along, I'm going to pretty much just minimize myself here and kind of talk along. And if you would just kind of write things as we go. First thing I want to talk about here is what momentum is. And you maybe have heard of momentum before. Usually we're thinking of an object that's moving and is coming at you, and it has a lot of momentum. So what, by definition, what momentum is, it is the quantity of motion an object has. And you're thinking, well, what in the world does that mean? An easier way probably to remember it is it's basically mass in motion. So, and we're thinking of an object coming at us and having momentum. We care about two things, really. In fact, this is what comes out in the equation is P, which stands for momentum, is equal to mass times velocity. So P is momentum, and then M is for mass, and then velocity. So we basically just multiply together the mass and velocity of an object to get our momentum. As far as units go, when we're talking about, I'm going to erase this a little bit here to give myself some space. When we're talking about momentum, the units we use kilograms for mass, and then we use meters per second for velocity. So this is what our units look like, is kilograms times meters over seconds, okay? So that's momentum. It's pretty simple. You just multiply mass times velocity of an object anytime you want to calculate momentum. Now, impulse has to do with, when you think of someone who is impulsive, usually they make quick decisions. And when we talk about impulse, it's all about putting a force on an object for a period of time. A lot of times it's a very short period of time. If you just push on something and then stop, the impulse is sort of a measure of how much force you're putting on an object for a given amount of time. So impulse, I'm going to erase what we have here, and that way I can kind of scroll down and give myself a little bit more space. See if I can get out of this. I'm going to scroll down a little bit, give myself a little bit more space here on impulse. So when we talk about impulse, we are talking about the product of the force acting on an object over time, over a period of time. And so as it turns out, we say impulse, which strange enough gets the letter J, not the letter I. The letter I was taken. We use force times a segment of time. So a lot of times you'll see it written like this. This is really just the force on the object times time. That's what impulse is, okay? Now, this is kind of derived from Newton's second law. If you remember what Newton's second law says, F equals ma, okay? And if you remember the fact that acceleration really is just a change in velocity over a segment of time, we can actually plug in this velocity over time change into acceleration, and force is equal to mass times change in velocity over a segment of time. Okay. And if I decide to get rid of that fraction, all I have to do is multiply both sides by delta t, and my delta t on the right side will cancel. And that's actually what equation we're dealing with here. Impulse, which is force times our segment of time, is actually equal to mass times our change in velocity. This is a really big equation that we're going to use in this unit, okay? The left side of this equation, that is impulse. The right side of the equation, if you look closely there, is mass times change in velocity. This is change in momentum. Sometimes we'll label it as delta P for change in momentum, but basically what it is the mass of an object times its change in velocity, okay? Now, this is all connected because if you put a force on an object for a period of time, it's going to cause a change in momentum for that particular object, okay? So let me kind of scroll down here and kind of put this into words for you. The impulse momentum theorem, which is kind of where we're headed for really most of the problems we do, is impulse causes a change in momentum. So if you see any problem that says use the impulse momentum theorem, what you're typically using is the fact that J, impulse, causes a change in momentum. That's really the main concept we're getting after. Well, we typically don't really use J and delta P because we actually want to turn this into force times our change in time is equal to mass times change in velocity, which a lot of times we will just relabel as this. V final minus V initial. For this right here is our change in velocity. It's a little more helpful to really put it in terms of V final minus V initial. That's really the main concept here that we're going to be using in this unit, is that a force times its time increment, the amount of time you put that force on something, you're going to cause a change in velocity. And we can use that equation actually to do a lot of the calculations we're going to do. All right. So let's go ahead and start working some sample problems. So the first sample problem we're going to do is, well, first two sample problems we're going to do right here should be really straightforward and easy. It says a 65-kilogram football player is running at a velocity of 7.5 meters per second. What is his momentum? Well, this is about as easy as we're going to get, in that to calculate the momentum of any object, you just multiply the mass of the object times the velocity. So we're going to go 65 kilograms, right, times the velocity of 7.5 meters over seconds. When you punch this into a calculator, considering they both have 2 sig figs, calculator gives you 490. The units really are just kilograms times meters over seconds. That's the momentum of your object, okay? Now, question 2 gets a little bit more within the changing of momentum. It says a 12.5 kilogram dog accelerates from rest to 9.5 meters per second. So we know that the dog has initial velocity of 0. The final velocity of the dog is 9.5 meters per second. If we want to find the change in momentum, we really need to do mass times change in velocity. Well, that's mass times the difference between the final velocity and the initial velocity, right? So the good news is the initial velocity is 0 since he's at rest. So to get our change in momentum, we're just going to take 12.5 times V final 9.50 minus 0. So as it turns out into a calculator, since he has no momentum when he starts, really we're just finding the final momentum, and that would give us the difference. So 12.5 times 9.50, we're going to go 3 significant digits here. So we're going to go 119, and that is kilograms meters per second. That is our change in momentum. Now it says, based on the impulse momentum theorem, what is the dog's net force if it takes 2.5 seconds to accelerate? So this is where I told you before, J is equal to delta P is really the concept. Well, we already know delta P. So what we have to do is turn J into really a more useful form. Force times change in time, or our increment of time, is equal to change in momentum. You could plug in mass and final and initial velocities if you want, but we already know our 119. So we're going to plug in the numbers we know. Force times 2.50, because that's our time increment, is equal to 119. You're going to divide both sides by the 2.5 to get force by itself. So in the calculator, 119 divided by 2.50, you end up with 47.5 newtons. So we're able to actually calculate what is the force or net force of the dog as it's accelerating based on this idea of impulse changing momentum. That is the impulse momentum theorem, okay? All right, let me clear what I have here and let's move on to the next problem, okay? Got a little illustration for you here. Basically, a child sledding down a hill, moving at a velocity of 5 meters per second. When he hits a tree, oh no. Okay, so a couple things we're going to do here. First part of the problem, it says, what's the momentum as he hits the tree? So if you think about he's moving at a velocity of 5 meters per second, we can just use this equation, 35.0 times 5.00, multiply those together. When you punch that into a calculator, you're going to get 175, and that is kilograms meters over seconds. That is the momentum of the child as he's about to hit the tree, or the instant he hits the tree. Now it says, what was his change in momentum when the tree stopped him? To get a change in momentum, you want to do mass times change in velocity, which is really V final minus V initial. Okay. So to get our change in momentum, 35.0 is the mass. In final velocity, since it stops him, is 0. The initial velocity is 5.00. When you plug this into a calculator, you're going to notice you essentially get the same answer, but there's one slight difference. There is a negative sign on here, okay? What that negative sign tells us is that the tree is pretty much pushing at him the other direction. So the change in momentum is back kind of up the hill or the opposite direction that the kid on the sled was moving, okay? So it is, think of it as taking away the momentum. So momentum is to the left this time and not to the right. So he's moving to the right. That's why he's 175 kilograms meters per second in momentum. And then the tree takes all of it away. So it's a change in the negative direction, okay? Now, this problem continues on the next page here. Let me kind of scroll down. It says, what impulse was required by this tree to stop the child? Well, impulse is J, or change in momentum. Well, to get him to stop, the tree had to put 175 kilogram meters per second on him to the left. So it's the same answer. So what impulse was required? Well, impulse is equal to that change in momentum. All right, now the fun question. If he stopped in a time of 0.500 seconds, what's the net force from the tree causing him to stop? So remember, according to the impulse momentum theorem, force times increment of time is equal to our change in momentum. Well, we know our change in momentum, delta P. We also know our time. So I'm going to divide both sides by this delta T. I'm doing this a little different just to get F by itself first. So force ends up being negative 175 divided by this time of 0.500. If you punch that into a calculator, you're going to get a negative 300. You want to put a decimal there. so that we have 3 significant digits. Whoops, not 300. It's 350. I misread that. So it's negative 350. We do want that decimal there. The negative really just says, hey, that's a force to the left. That's what that negative sign means, okay? All right, moving on. Last problem. We have a little bit of a basketball bouncing problem, okay? So we have a basketball that is being dropped from a height of 1.50 meters. And we're going to figure out several things here. The first thing we're supposed to find out is to calculate the gravitational potential energy at the top of the drop. So if you look closely here, we're dropping it from 1.5 meters. So to get the initial gravitational potential energy, we just use our GPE formula. So we can take the mass of the basketball, 0.625, multiply by 9.80, and then the height, 1.50 meters. When you plug that into a calculator, you're going to end up with 9.19 joules. That's how much gravitational potential energy the ball has when we let go. Okay. Now it says, what is the kinetic energy of the ball as it hits the ground? So as the ball falls, all of its potential energy is going to change into kinetic energy. So here's the concept, conservation of energy. All of the potential becomes kinetic energy. So we end up with 9.19 joules of kinetic energy the instant it hits the ground. Okay. Now, the next part of the problem is to calculate the velocity of the ball as it's hitting the ground. Well, we know how much kinetic energy it has, 9.19 joules. What we need to do is set that equal to 1/2 mv squared, okay? And we've done this multiple times. I'm going to get rid of my fraction. So I'm going to do 2 times 9.19, that's my kinetic energy, divided by the mass, which is 0.625. That would be equal to v squared. So I have to square root this to get it equal to v. If I punch this into a calculator, 2 times 9.19 divided by 0.625, get that answer, and then square root it. Calculator gives me 5.42 meters per second, okay? Now, here's what the calculator doesn't do. The calculator does not consider direction. Since we know the ball is downward, this is a little bit tricky, we're going to throw a negative sign on here. This is going to be really important. When the ball changes directions, we really have to pay attention to the fact that this was a downward moving ball. So we're going to say that the velocity is negative 5.42 meters per second the instant it hits the ground. Okay. Next problem. It says if the basketball bounces off the ground with an upward velocity, notice I've got a plus sign on there, of 4.95 meters per second, and the floor puts an upward force of positive 64.8 newtons on the ball. How long is the ball in contact with the floor? Okay, so here's how we're going to do this problem. Impulse momentum theorem, the force times the time increment is equal to, you can either put delta P here, or what's probably easier is using the mass times our final minus initial velocity. Okay. You have to pay really close attention to signs here. Okay. What are we trying to find? We're trying to find delta T. Okay. So I'm going to plug in everything I know. So my force is 64.8. That's positive. Delta T is my unknown. My mass is 0.625. And then tricky, be careful here. V final, that's the upward velocity, is positive 4.95 minus the initial velocity is negative 5.42. You have to be careful here because of the signs. So when I get my calculator out, I'm going to do what's in parentheses first. 4.95 minus a negative is just like adding 5.42. My calculator tells me 10.37. I'm going to multiply that by 0.625. And I'm going to put kind of an intermediate number here out to the side. So we really have 64.8 T or delta T. I should keep my delta T in there. Delta T is equal to this 6.48125 I got on a calculator. So we're going to divide both sides by this 64.8. Okay, and that's going to give me my delta T by itself. So divide by 64.8, I get 0.100, I'm going to go 3 sig figs here, seconds. So it's basically a tenth of a second that the ball must be in contact with the floor, okay? All right, let me clear these slides. Scroll down. Last question, okay? Based on the upwards velocity, the ball leaving the ground, how high will the ball bounce? Okay, well, here's what we know. We know that the velocity as it leaves the ground is, what did we decide it was? 4.95 meters per second, right? Okay, so what we really need to do is we need to calculate the kinetic energy as it leaves the ground. 1/2 mv squared. Notice I'm not putting initial and final because it does get a little confusing. This is sort of the on its way back up at the ground level after it hits the floor. So what I'm going to do is I'm going to calculate based on that velocity what my kinetic energy is. 1/2 times mass times 4.95 squared. That's going to give me my kinetic energy of the ball as it's leaving the ground. So 4.95 square it times 0.625 for the mass times 0.5. I get 7.66 as my kinetic energy. Okay, that is as it's leaving the ground. So what we do is we say based on conservation of energy, the kinetic energy will turn into gravitational potential. And so we're going to say mgh. I'll call it final there. That's our endpoint. So we know that we're going to have still 7.66 joules of energy. The mass is still 0.625. We're still using 9.80. We really are just finding the new height. So if I take my calculator, I kept my number in it, divided by 0.625, divided by 9.80, we get a height of 1.25 meters. Okay, now if you look closely there, that's different than the drop height. We started at a height of 1.50 or 1.5 meters. Notice it doesn't return to the same height. And this is more what we see as normal. What's happening here, and we'll talk about this a little bit more in this unit, is some of that energy in the contact or collision with the floor, some of that energy is lost or dissipates into a different type of energy. So we don't actually have, with the collision of the floor, we don't have full conservation of energy, and that's why it doesn't bounce back up to the same height. Once you get done with these notes, go ahead and submit them to Canvas. All right.